Hey there everyone, welcome to another episode of HET. So this is week 2 of our educational series on electricity. Last week we talked about charged particles like protons, electrons, and how the forces between those electrical charges, which is one of the fundamental forces of the universe, is defined by Coulomb's law, which states is that the magnitude of the force between any two charges is equal to Coulomb's constant times the value of those two charges, Q1 and Q2, divided by the distance between the centers of charge squared. Okay. But this week we're going to talk about how each of those charges generates fields and how we can calculate the strength of that field at any given point, regardless of how many charges there are. So to start off, we've got our proton here. P. And he's going to have, field lines coming out of him in all directions. So right, left, north, south, east, west, everywhere, up, down. And because he's positive, we're going to show these field lines as pointing outward. And the thing to notice about these field lines, as I keep on drawing more of these things, is that if we were to draw, a circle at any given point, so let's say we draw a circle here. So here, inside this circle, we only have one field line. But if we draw, and I'm just kind of making the assumption that all of these lines are relatively equally spaced. But if we draw a circle of the same size right here, we have 3 field lines. So from this we know that the strength of the field is going to be somewhat related to the distance from which we are from this charge, and that's going to be evident in our equation for the strength of these electric fields. Let's use a bigger marker, which is going to be E. That's what we're going to denote as the strength of our electric field, is going to be equal to, again, we're going to use Coulomb's constant. But instead of having, 2 charges, we're just talking about one charge here. So it's just going to be equal to Q, so the amount of charge, divided by R squared, sorry. Okay. And that's going to be in newtons per Coulomb. Now, what if we had, let's say, 2 charges? So we'll draw, proton here. And we'll draw an electron here. These aren't necessarily to size. So what happens with the field lines now? So these fields are going to kind of affect, well, they're not going to really affect each other, but we can consider the space around them is going to be affected. So if we were to draw our field lines to see what the surroundings are feeling as a result of the fields coming from these 2 independent charges, we're going to have a really dense field in between them, because we have 2 charges, So we have a lot of fields going on in here. And we're always going to draw, our field lines is going from positive to negative. So here, this is a proton, so all the fields are going out. So electrons, because they're negative, are going to have all their field lines pointed inward. But so we have one field line here, and again, like we said, this space in between here is going to be very densely populated with field lines. And then we're going to get gradually weaker as we get farther and farther away. Field lines to immediately to the right or left aren't really going to be affected. Only in such that, they're not going to be quite as strong. And he's just kind of going out into space. He's just kind of going out into space. Eventually, he'd probably terminate over somewhere there. Okay, but that's what kind of what our field would look like if we had, a proton and electron, pretty close to each other. Now, if we had two electrons, those fields are going to repel each other. So we're going to kind of have an opposite effect. So in this situation, we're actually going to have no field in the middle because like those field lines are repelling each other. And so all the field lines are going to kind of go up, and then we kind of have this imaginary line in the middle. Oh, I'm sorry. All these arrows should be pointed. Man, how embarrassing. Yep. So again, because these electrons are negatively charged, all these field lines point to charge. Okay, fix that. Anyway. But yeah, so let's shift gears here. Let's say we want to know exactly what, the charge is, given our proton and electron situation here for a given point in space. So we're going to draw a coordinate system. So we got our y-axis right here. X-axis is going to be right here. And we're going to say 3, 0. So 1, 2, 3. We're going to have an electron. And at negative 3, 0, so 1, 2, 3. we are going to have a proton. And we want to know the strength of the field at this point in space 1, 3. So we're trying to figure out the point in space, or the strength of the field at this point in space as a result of these two charges. So again, if we were to draw our field lines, it would look something like this. The arrow's pointed this way. I keep on getting my field lines mixed up. Okay, I think that's right. Yep. So we can already tell just by drawing our field diagram here that, it's probably pointed, somewhat in this direction-ish. But we don't have any calculation for that yet. But we can figure that out, and we can figure that out no matter how many charges here we have, because the net electric field, E, is going to be equal to the sum of all of our charges. So in this case, it's going to be equal to E1 plus E2. So again, it's going to be the charge at this point in space here is going to be equal to, the effect of this charge and the effect of this charge. You can sum them together and get the net field. And you can get the direction as well. So if we go about doing this, first we're going to just kind of focus on the magnitude of the charges. So we're going to split each of these into their x and y components. And we're going to use some trig. If you get triggered by trig, don't worry, I'll start drawing some diagrams and walk you guys through it. But like I said, before we do any of that, we need to figure out what the magnitudes of these charges are. So we got our equation here. E1 is going to be equal to, Coulomb's constant times the magnitude of Q1, which is positive because we have a proton for our first charge, divided by the distance between that point in space and the center of our charge, Q1. Okay. So from that, we know that E1 is going to be equal to 9 times 10 to the 9th. Again, that's in newtons times meters squared times coulombs to -2 times the magnitude of our charge, 1.6 times 10 to the -19th coulombs, all divided by r squared. Sorry guys, this should have been squared right here. Okay, but we're still on the right track. So how do we calculate, the distance between our center of charge here and this point of space here at 1, 3? Well, we use trig, that's how. So using, our Pythagorean theorem, we know that R1 is going to be equal to R1x squared plus R1y squared, and then take the square root of all of that. So that is going to be equal to, see, we got 1, 2, 3, 4 for our x component. So 4 squared. And then 3 up for our y component, so 3 squared. And this is actually known as one of our magic triangles, so we know that the hypotenuse is equal to 5. If you don't believe me, you can calculate it for yourself. Anyway, so that's what R1 is. So we can plug that into our equation up here. That's in meters. And we get that E1, so our electric field as a result of, our proton right here, is equal to 5.76 times 10 to the -11th newtons per coulomb. Okay, and that's just the magnitude, right? So we don't know the direction of this yet. But we can figure that out. But before we do that, we're going to kind of break this down into our x and y components, so we know that E1x, so the x component of this guy, is going to be equal to E1 times the cosine of our angle theta. So theta 1. So here, if we were to draw our triangle, from our proton here, center of charge, to that point in space, we're looking for this angle theta right here. Zoom this in a little bit so you can see it a little better. So we're looking for this angle right here. And, going back to, our trigonometry, so if we got a right triangle here, right, it's a right angle. So this is our hypotenuse here. And then this is going to be this is the angle that we're concerned with here. This is what we're trying to figure out. So this is our opposite side. This is our adjacent side. And cosine is always going to be equal to our opposite, or adjacent. Sorry, even I get confused, trig. So it's going to be equal to our adjacent length here divided by the hypotenuse. So in this case, we don't actually need to know what this angle is, since we already know what this component is here and what this component is here. So we know that we're going 3 up, 4 across. We can just use that to say that this is going to be equal to E1, which is 5.76 times 10 to the negative 11th newtons per coulomb, times 3 divided by 4, right? So this is the same thing. This is what our cosine effectively is. Or not 3 divided by 4, 3 divided by 5. Okay, and that is going to be equal to 4.608 times 10 to the negative 11th newtons per coulomb. Okay, and then similarly, E1y is going to be equal to E1 times the sine that angle theta so we have our charge here, which is 5.76 times 10 to the negative 11th, and we know that sine is equal to opposite of our hypotenuse. So here we know that's going to be equal to, we're going up 3 over 4, and this we figured out from our trigonometry or Pythagorean theorem that this is equal to 5. So in this case, it's going to be equal to, I'm sorry, this was 4 over 5. This is 3 over 5. Which is equal to 3.456 times 10 to the negative 11th. Again, this is newtons per coulomb. Okay, so we got our x component as a result of the charge here from our proton, and then we got the y component as well as a result of the field from this proton here. So now we're going to try to figure out what our fields are as a result of this electron here, because then in the end all we're going to do is just add them together. And the result of that is going to be our net effect for this point here. All right, so E2, or the magnitude of E2, we can draw it blue because we're dealing with our electron here. It's going to be equal to Ke times Q2 all over R2 squared. That's going to be equal to 9 times 10 to the 9th newtons times meters squared times coulombs to the negative second times a negative 1.6. So now here, this is where our signs start to become important because we're also trying to figure out the direction of this charge. We have to take into account whether or not we're dealing with a positive charge, in which case the charge is going to be positive, or if we're dealing with a negative charge here, in in which case this charge is going to be negative. So we have our negative 1.6 times 10 to the 19th, negative 19th coulombs, all divided by R2 squared, and R2 is going to be equal to, so we're going back 2, so we have square root of 2 squared, we're still just going 3 up, plus 3 squared, which we're just going to draw as the result of root 13. It'll make our calculations easier when we go, and then we can just plug them into our calculators later. All right, anywho, so that's equal, and here, because this is squared, we can just say it's a regular old 13. But we do have our meters squared. Okay. Anywho, now we're trying to divide this into the x and y components. So in here, again, the direction is going to be important as well. So we have E2x is going to be equal to E2 times cosine theta 2. What is this angle theta 2? So we look back here. So all of our angles are going to be the angle that would be drawn if we, go from this first quadrant here and then around counterclockwise to our point here. So this angle theta 2 is going to be this angle here. So this is theta 2. Okay. And this is where our, signs of our direction. So we can draw that as, 2 times negative. So if we're drawing our triangle here, so the magnitude of this is going to stay the same. This is going to be root 13. But this distance here, this is where our sign is going to be important again. So we're going to have a negative 2 because we're going to back from our electron. This is our point in space here. But then we're still going to have a positive 3 here. All right, so when we're drawing out our cosine equation, we're going to basically just draw E2 times negative 2 over our root 13. Okay, so that's going to be equal to positive 6.144 times 10 negative 10 or negative 11 newtons per coulomb. So, but our electron's negative, you say. So how do we end up with a positive number here? Well, so if we go back to calculate what our magnitude of E2 was, or not magnitude, I should say, because we're actually calculating, the net result. E2 is going to be equal to negative 1.108 times 10 to the negative 10th newtons per coulomb. So because we have that negative here as a result of the electron, but then we go back, we end up with a positive number. Okay, so then E2y is going to be equal to E2 sine theta 2, which again is going to be equal to our negative 1.108 times 10 negative 10th newtons per coulomb. And then here we're going to have 3 over root 13. So here we are going to have a negative number because our sine of our angle theta 2, which again is this angle right here, is still positive. So we have the result with a E2y of negative 9.217 times 10 negative 11th. Okay. So now we finally get to put all of this together. All right, so our resulting EX is going to be equal to E1x plus E2x, which just plugging that into our calculators is going to give us, we can write it out. So we have 4, what do we have? Yeah, so we had 4.608 times 10 negative 11 newtons per coulomb plus 6.144 times 10 negative 11th newtons per coulomb, which results in an EX of 1.075 times 10 negative 10th newtons per coulomb. And we're going to do the same thing for EY equals E1y plus E2y, which is going to be equal to 3.456 times 10 negative 11 newtons per coulomb, plus a negative 9.217 times 10 the negative 11th newtons per coulomb, which is going to give us an EY equal to negative 5.761 times 10 to the negative 11th newtons per coulomb. Okay, so we know the x component of our field at this point here, and we know the y component. So with that, we can actually determine both the angle of the field at this point here and the magnitude. So to figure out the angle of our field at that point, so we're going to say the angle of our field E is going to be equal to the inverse tangent. So again, so drawing our right triangle here. This is our right angle here. Tangent. So we got our hypotenuse. Let's say this is our angle, theta. So tangent would be equal to opposite over adjacent. And here our adjacent would be our x component, opposite is going to be our y component. So this is going to be the inverse tangent of our y component, which is negative 5.761 times 10 negative 11th. We're just going to leave the newtons over coulombs out of it because they're going to cancel. Over 1.075 times 10 negative 10th. Which equals a negative 28.18 degrees. So that's kind of close to what we were kind of estimating with our diagram here. So this angle, it would be kind of be negative, you know, from this axis here. So that's what our is going to be our negative. What would we say? 28.18 degrees from the horizontal. And we know that we don't have to add 180 degrees from this because our y component here is negative. All right, so if this was positive, then we would have to add 180 degrees. Or no, we know that because our x component here is positive. If this were negative, then we would have to add 180 degrees. All right. So we know that our angle here is 28.18 degrees. What is the magnitude? And this marker's dying. Of our field at this point. So our magnitude is going to be equal to our x component, or the square root of ex squared plus ey squared. So again, we're just doing Pythagorean theorem here. So our magnitude of E is going to be equal to square root of 1.075 times 10 negative 10th squared plus negative 5.761, and this negative doesn't really matter because we're squaring it, times 10 negative 11th squared times an angle of 28.18 degrees. So this gives us E1 is equal to, or E, sorry, it's a long lesson. It's equal to 1.22 times 10 to negative 10th newtons per coulomb at an angle of 28.18 degrees. Now another way to write this, we could say that the E, if we just wanted to keep it in terms of the x and y components, we could say that E is equal to a to 1.075 I. So that's just a fancy saying of this is our x component of this vector here. So we're just writing this in vector form. Minus, because we have a negative, 5.761 J. And here this would be times 10 negative 10th. This would be times 10 negative 11th. Okay, that's it, guys. That's how you calculate, and we could do this for any number of, charges, so we say we had another electron here, proton here. We could divide, all of those the fields due to those charges into their respective X and Y components, and then add all those components together to find out what our net field is at this point here. So thanks for sticking with me through this. I know this is kind of a longer lesson. The next lesson will get a little bit more interesting when we're going to talk about, electric potential and voltage. And then hopefully start digging into a little more current type stuff down the road. So thanks again, guys. Give this video a like if it helped you at all in terms of your electrical understanding. And remember to subscribe.